Hello and welcome to Electromagnetics 1. This is lecture number 5. This is the first lecture in this course that is going to deal specifically with electromagnetic theory. We're going to start with electrostatics. Specifically, we'll be talking about Coulomb's law and continuous charge distributions. Well, the place to start, in my view, with electrostatics is with Maxwell's equations themselves. What you're seeing here is the full vectorial Maxwell's equations basically in the greatest generality that you'll typically find them. This is the differential form. In other words, we're dealing with derivatives, not integrals. But nonetheless, we have four of them. We have Faraday's law, Ampere's law, Gauss's law, and Gauss's law for magnetic fields. And if you'll notice, in the most general case, the fields depend both on position and on time. Well, let's see what happens if we consider the time-invariant case. In other words, if we allow all of these derivatives with respect to time to go to 0. Let's see what happens. Well, clearly this term is going to fall out. We're going to have a 0 on the right-hand side here of Faraday's law. And similarly, this term right here is also going to be 0 on the right-hand side of Ampere's law. The consequences of allowing, I should say of considering the time-invariant case, in other words, of setting all those time derivatives to 0, are the following. The electric and magnetic fields decouple. What does that mean? Well, if we're interested in electrostatics, which is where we're going to be starting today, the two equations that involve the two Maxwell's equations from the previous slide that involve the electric field are here. Okay, the curl of the electric field is 0 and it no longer depends on time, and the divergence of the permittivity times the electric field is equal to the charge density. Okay, the volume charge density. The electric field is only produced by electric charges. In other words, this charge distribution here produces the electric field. If there is a magnetic field, it doesn't have anything to do with the charge distribution. In other words, this electric field here does not depend on whatever magnetic field may exist due to, over here on the magnetostatic side, if you go back to those previous slide and gather the two equations that involve the magnetic field, it's this one. This is Ampere's law. This magnetic field here is generated only by this magnetostatic current. Okay, steady state current. In other words, I should say a DC current really is. Excuse me, a DC current. This DC current generates this magnetic field. The magnetic field does not depend on the electric field. It doesn't depend on the charge distribution. It just depends on whatever impressed current may be there. Okay. The magnetic field is produced, we would say, by electric currents only. So when there's no time dependence, when we're talking about the time-invariant case, we can study the magnetic field in isolation from the electric field and vice versa. Well, the first stop on the track here for electrostatics is Coulomb's law. Okay, and Coulomb's law deals with a very simple situation. We have 2 point charges, Q1 and Q2, located respectively at some position R1 and R2 in three-dimensional space. Okay. And Coulomb's law states that the force F felt between 2 point charges Q1 and Q2 is the following. It's directed along the line joining them. Okay, if you notice, this is the force on the second charge due to the first charge, and you'll notice it is lined up with a vector pointing from the first charge to the second. Secondly, it's directly proportional to the product Q1, Q2 of the charges. Okay, so the magnitude is directly proportional simply to the product of the two charges. And thirdly, I should say, it is inversely proportional to the square of the distance r between them. So if we look at this distance here between Q1 and Q2, the force felt by the second particle due to the first is inversely proportional to the square of the distance. We write that mathematically in this way. The force is proportional. This is just some proportionality constant k here. It's proportional to the product of the charges and inversely proportional to the square of the distance between them. Now, we can actually make a vector out of this force in this way. This again, F12 right here. This is the force felt by the second charge due to the first charge. It's equal to the product of the charges divided by 4 pi times the permittivity times the square of the distance. And it points in the direction of a unit vector here that points along this line right here, r sub 1, 2. Okay. Now, a couple of important things to notice here. If both charges have the same sign, then the force is going to be these charges are going to experience a repelling force, a force that pushes them away from each other. So if both Q1 and Q2 are negative, they will repel each other. If both Q1 and Q2 are positive, they will repel each other. The only time that we get an attractive force, you can see, is if the sign of one of these is different from the sign of the other charge, then F12 is going to turn around and point in this way, and we'll get attractive forces. So opposites attract, like charges repel. Well, what happens if we have an arbitrary number n, say, of charges distributed in space? The principle of superposition states that if you have n charges, Q1 to n, located respectively at points with position vectors r1, r2, etc. up to n, the resultant force, F, on a charge Q located at some other point r is the vector sum of the forces exerted on Q by each of the charges, Q1, Q2, and up to Qn. Okay. In other words, if you have 3 charges, and so R1, R2, and R3, and you want to know what is the force that a charge Q located at R feels, you just simply sum up vectorially the contribution to each of those 3 charges at that point in space. Mathematically, that looks like this. We say, again, this is the force felt by charge Q out at some point R in space. Okay. So it depends on its own charge, the charge that it carries. That's no surprise. And then you can see here it points along. This is a vector. Okay, I should say it is the vector sum of a vector that points from each charge to that point. Okay, so it's pointing from each charge to that point. And the magnitude, again, it's a little hard to see here because I'm not using unit vector notation, but the magnitude of that vector falls off as the square of the magnitude of the distance between them. Okay, so it is proportional to 1 over r squared, just like we saw in the previous slide. Okay. At this stage, we have a way to notionally define what the electric field means then. Okay, so if this is the force that a charge Q feels due to all the other charges around it, then if we simply divide that force by the charge itself, we arrive at the electric field. So the electric field intensity, the strength of the electric field, is the force that a unit positive charge experiences when placed in an electric field. So if we were to take a charge with 1 Coulomb on it, plus 1 Coulomb, and we were to place it in an electric field, the electric field intensity at that point tells you how hard, how much force the charge at that point would feel, a unit 1 charge would feel at that point. Okay. Well, generally speaking, not only can we have discrete distributions like we had due to point charges, but we can also have what are called continuous distributions. Okay. A continuous charge distribution is essentially a distribution that varies continuously in space. In other words, you need an integral to represent the electric field due to a charge distribution, where before we had a sum. If you'll notice here, the force due to these discrete particles at endpoints is a sum. When we pass to the integral here, you'll notice, I should say, when we pass to a continuous distribution, then this summation becomes an integration. What I want you to understand, though, is that qualitatively, again, if we were simply to divide through this, both sides of this expression by Q, we would have the electric field, right? So in some senses, this is telling me what the electric field due to these end charges are, and point charges are. This formula here, this formula right here, is completely analogous to these formula right here. Okay, so I don't want you to lose the intuition just because we're now passing to a continuous distribution. In other words, a distribution that you need an integral to understand and to describe. The exact same thing is happening. Okay, the exact same thing is happening. Let's look at the case, say, of a surface charge. All right, we'd like to know what is the electric field at a point R out here in space due to, let's call this region, let's say this region is a surface charge. So we're going to say this is rho sub s now. So this region is filled with charges that are distributed continuously over this surface. Okay, and we would like to know what the electric field is out here at this point R due to these charges. Well, let's suppose that all the charges here are positive. They're positively charged. They're positive charges that are distributed over this surface. Okay, so if you'll notice what this equation is saying, is that a little differential piece of charge, that's given by this expression right here, the charge density times ds prime. Okay, so a little differential chunk of charge located here at r prime, right here, produces a differential electric field that points in this direction along capital R here, which is r minus r prime. That's what this expression is saying. If you'll notice, see, this this vector r points from wherever we are on the surface, wherever we're at the point at which we're integrating, to the observation point. Okay, and it falls off again as 1 over the magnitude squared. It looks like 1 over the magnitude cubed here, but remember, this is not a unit vector. So if we made this into a unit vector, we would have 1 over r squared there in the bottom. Okay, but the important thing is, as I was saying, is to understand that even if you have a continuous distribution, the same physics is happening. Each of these little chunks of charge are acting independently, and if we want to know what the total electric field is, we just add up the contributions due to each of those little differential chunks of charge at this point here, R. It is a vector, though. Each little differential piece of charge creates a differential vector field right here for the electric field. Okay, let's see how this would work for a practical problem. Let's say that we have a finite line charge. Okay, this is example A in the Satiku text from chapter 4, and I'm going to turn on my Elmo here, and we'll step through this example slowly together. But here's the basic situation. Okay, you've got a line of charge that exists right here from point A to B along the z-axis. So they tell you in your text that the charge density is constant. It's not a function of position, but you have some linear charge distribution right here that's distributed from A to B along the z-axis. Okay, and the question is, what is the total electric field due to this entire charge distribution out here at this point R? Okay. We'd like to know what is the electric field due to this charge distribution at this point right here, R. Okay. I have to go to my Elmo here just momentarily. Let's see. All right, so let's have a look. To flip this around. Let us have a look together here at this geometry one more time. Zoom in just a bit. I need to scoot this over so I don't make sure that I don't get my face in the way as well. Okay, once again, this is the geometry of interest right here. Line charge located along the z-axis and distributed between A and B. Okay. Well, let's look at the governing equations for this situation. So the most general equation that we have to deal with is right here, right? This is one of the equations from the previous slide. The electric field at a point R due to a linear charge distribution is given by 1 over 4 pi epsilon times the charge distribution times a differential length divided by the cube of capital R pointing in the R direction. All right. So the challenge is if you remember from the previous slide, we had two coordinate system, an unprimed coordinate system, that is the observation point right here, okay, and a primed coordinate system that travels over the object as we do our integration. Okay. So let me show you concretely here for this problem how to come up with expressions for each of these pieces. We're going to need an expression for little r. We're going to need an expression for rho l. We're going to need an expression for r prime, for dl prime, and for capital R. The magnitude of capital R and for capital R as a vector. Okay. So for this particular geometry, again, you'll have to refer back to the picture I just showed you. What we're going to allow dl prime to simply be dz prime. Okay, so we're just integrating along the z-axis, right, from A to B. So our differential length is just simply dz prime for this problem. Okay, now R, capital R, is our observation point, and for this problem, our observation point is just located at rho in the rho hat direction plus z in the z hat direction. So the sum of these two terms right here, this is little r, our observation vector. Okay, and then our primed coordinate points from the origin to a point on the charge distribution. Okay, and for our purposes, that is just simply the vector z prime in the z direction. Okay, that vector points from the origin to a point on the charge distribution. Okay, and so R is the difference. Capital R is just simply the difference between R and R prime. So this vector minus this vector, which we can write in this way. All right, capital R is rho hat plus z minus z prime times z hat. Okay. So another term we need here in this equation is the magnitude of capital R. We find the magnitude of capital R by just simply, the square of the magnitude is just the square of the components. So from this component we get rho squared, from this component we get z minus z prime squared. And so therefore the magnitude is the square root of those two squares, just like that. Okay. Now we're in a position to come right back here and substitute in for each of these terms in our original most general expression. Okay, so here we go. The charge density along the line is a constant. It's told we're told that in the problem, so it comes out of the integration, and we have 4 pi epsilon right here, 1 over 4 pi epsilon. Okay, we're integrating from point A to point B, wherever those happen to be, along the z prime axis. So here's our dl prime. It's just dz prime. We make that substitution. Okay. Then we have to put up here the vector capital R. That's what we calculated here. So that goes right here. This is capital R. And in the bottom, we take the magnitude of R to the 3rd power. Here's the magnitude of R. It's rho squared plus z minus z prime squared to the 1/2. So R to the 3rd is rho squared plus z minus z prime squared to the 3/2. Okay. So this is the integral that we now need to compute in order to find the electric field due to that continuous charge distribution out at a point R in space. Well, in order to compute the integral, we need to use the following trigonometric substitution. All right, and this is a kind of trick. I'm refer you back here to the original diagram again here. We can't do the previous integral in Cartesian coordinates very well. So what we're going to do is we're going to define an angle alpha right here. If you'll notice, here's alpha. Alpha just simply is the angle basically between rho and this capital R vector right there. That's what alpha is. And so we're going to introduce this alpha angle in this way. And if you'll notice, tangent of this angle alpha is z minus z prime. That's this distance divided by rho. That's this distance right there along there. Okay, so that's what's going on with this first expression right here. Tangent of alpha is z minus z prime over rho. We're making a trig substitution here. Okay, that implies this equation, which we'll need momentarily. Also, you can see pretty clearly here that cosine of this angle is rho over the magnitude of capital R. Therefore, capital R is rho times secant of alpha. Okay. So just remember, this is the geometry. This is the angle we've introduced, and alpha 1 is the angle that this initial R vector will make when you're starting basically at the bottom of the charge distribution. And then alpha 2 here, that's the angle that you get when you're at the end of the charge distribution. So alpha 1 and alpha 2, that's going to become the new limits of our integration. We'll see that in just a moment here. Okay, let's go back to this now. Okay, so we've made this trig substitution here. There's a couple of other little observations that we can make. Rho, again, just referring to that diagram, you can just see that the rho direction is capital R times cosine of alpha, and capital R itself is rho secant of alpha, right? We already saw this expression. That leads to this. And now, if we take differentials of both sides, you can see dz prime is equal to minus rho secant squared alpha times d alpha. Okay, this will help us to change variables in our integral. All right. So the first step is to go back in and simply substitute for rho using this expression, and substitute for z minus z prime using this expression in our original integration, or I should say in our original integral. Okay. So if we go back, and here is our original integral, and I've substituted in for rho and z minus z prime using those expressions that I just mentioned. So in the numerator we have these terms, in the denominator we still have r to the 3rd, and I still have dz prime in there for now. We're still integrating over dz prime. Okay, but you can see we've got a common factor of r that's going to fall out, and we'll just end up with this, with just r to the r squared now, I should say, in the denominator. Okay, the next step is now to go in and substitute for r and dz prime using these expressions right here. This is our expression for r. We're going to make this substitution for r, and we're going to make this substitution for dz prime. Okay. After we make those two substitutions, now we're, instead of integrating over z prime, now we're integrating over our new integration variable here, d alpha. And you can see we're starting our integration again at alpha 1, we're ending it at alpha 2, and we have this expression now underneath the integral sign. Happily, this secant squared alpha in the numerator cancels with this secant squared alpha in the denominator. We'll have a 1 over rho that still survives, but rho is a constant with respect to the integration over alpha, so it just comes out front, and we're just left with this very manageable integral over alpha. We just basically have to integrate cosine of alpha for the rho component and integrate sine of alpha for the z component. Once we actually carry out this integration, we arrive at the following expression right here for the electric field. It's equal to the charge density divided by 4 pi epsilon times rho times this expression in the rho hat direction and this expression in the z hat direction. So in the end, the electric field, due to a finite charge distribution, is inversely proportional to rho, to the distance from the z-axis, essentially. It's inversely proportional to rho, and it depends on, it shouldn't be too surprising either, the angle where you start and the angle where you end. Now, what I would like you to do as an exercise is to take this expression and to find out what the electric field at a point r is due to an infinitely long line charge. That's your homework for next time. Okay, I think that concludes this lecture, and I'll see you in the next one. Thanks for watching.